SwayamPrabha. Digital India. Educated India.
Hello everyone. So towards the end of last class, we were discussing accuracy as a criterion for appraising these models, right? And we talked about how accuracy is absolutely desirable. And where does accuracy come into play? We are trying to compare calculations, model predictions versus experimental measurements. And how close do they match to the experimental measurements? That determines the accuracy of your model. So the fact that you will have some issues with accuracy, we talked about an example, right? The boundary conditions and where do these accuracy issues stem from? That's the question. So these boundary conditions in the calculations need not correspond exactly to the experimental measurement. And we talked about an example, right? So the flow might be approximated as 2D, whereas experimentally there is nothing called 2D, it's always 3D. The boundary conditions on certain properties would not necessarily be known, so they have to be estimated from experimental data. So, and then I talked about a jet calculation, a turbulent jet calculation, where if you have experimentally a turbulent jet, and then you will have the pipe before the nozzle that creates this jet, and the pipe would be relatively long in order to have your flow transition to turbulence. But computationally, to do that, it would be extremely expensive to have a really long pipe and simulate the flow through that pipe so that the flow transitions to turbulence. So we only include part of the nozzle in your computational calculation. And I talked about how inclusion of the nozzle is a relatively newer norm that is in jet calculations, in turbulent jet calculations, where it is now known from literature that the nozzle needs to be included. Okay, now with that, we talked about how if in order to get the exit velocity, right, or the inlet velocity into the nozzle, where do you get that from? You want it to be turbulent. That profile has to be obtained from experimental measurements. When you get that profile from experimental measurements, is it going to be the mean profile that you use? Or are you going to be you cannot use the instantaneous, or are you going to be using the mean plus some fluctuation determined by the RMS of the velocity obtained from the experiments? Now, why only restrict yourself to RMS? Why not go to third order? Why not go to fourth order? Right? So you will have to make some approximations there. You have no choice. And these approximations, the real question here is, these approximations, do they affect the accuracy of your calculation? Because your boundary condition itself is something that you are using, which is very different from the experimental measurement. So your predictions or calculation results are going to be different, right? How much different they are, what is the influence of these boundary conditions in the actual flow is hard to say beforehand. So this is where the issue, this is one of the areas where the accuracy issue can stem. Now, the discrepancy between the measured and calculated properties arises, one, because of the inaccuracies of the model, okay, meaning is it a very accurate model, or is it a mixing length model or a DNS, right? So the discrepancy between measured and calculated flow could come from that. That's one. Second is numerical error. Now you're using a numerical method to solve your equations. If you use a numerical method, there is going to be a truncation error associated with that numerical method. So how much is that truncation error? Can you refine the grid very fine such that the truncation error becomes very negligible? But the cost associated with increasing the number of grid points is also going to shoot up quite high. So then you are limited by that. So your computing resources, the limitation in computing resources also affects the accuracy. because your grid cannot be fine enough, and that depends on your numerical method, right? So that's the second part. The third is the measurement error. So in other words, we don't touch upon this often enough, but there could be an error in the way you have measured the velocity from the experiment. So maybe you're trying to match something that is not matchable, in the sense that experimentally there might have been some discrepancies or inconsistencies in the way you measured your flow velocity, for example. And fourth is the discrepancies in the boundary conditions. So the earlier example, as far as the nozzle exit velocity example that I gave earlier, is one example of that, where you could have a discrepancy in the boundary condition itself that would lead to inaccuracies. So these are the four sources essentially of inaccuracies. Four sources of inaccuracies. One is there could be an inaccuracy associated with the modeling approach itself, like the mixing length model. The mixing length that is specified, that is obtained from boundary layer flows. Does it apply to jet flows? There could be an inaccuracy there. Second is a numerical error, something like a truncation error, that is associated with the numerical method. Third, the measurement error itself, although chances are that is going to be the least determining factor, mainly because experimental errors are in general rare compared to errors that stem from computation. That is the general norm, right? If you're doing your experiment properly, your experimental measurement is going to be accurate. Fourth, discrepancies in the boundary conditions. So that's here it could be because some data for the boundary condition that you need to apply in the computational in the computations is just not obtainable. You cannot get that data, so then you have to approximate, right? 2D versus 3D is another example. So final point here is the truncation error definitely scales as a positive power of x. So if it is second order, it is delta x squared. If it is third order, it is delta x cubed. So if you reduce your delta x, your truncation error is going to reduce. But keep in mind, the computational cost also increases with 1 over delta x as a positive power. So then that limits the number of grid points you use. So that affects your accuracy, right? Okay. So now that we have looked at the 5 different criteria, let's look at the most accurate approach out there, which is direct numerical simulation, or DNS. So as you all know, DNS solves the Navier-Stokes equations exactly. It resolves all length scales of motion with initial conditions and boundary conditions. And here, each simulation basically produces a single realization of a turbulent flow, right? A single realization of turbulent flow. What do I mean by that? Single realization means if you carry out your experiment once, that's your single realization. Now, until about 30-40 years ago, DNS was just completely not possible because computing power was not available at all at that time, right? So until about 1970s, you couldn't even think of a DNS. Now, conceptually, if you think about it, it is the simplest approach because all you're doing is solving the Navier-Stokes. All you need is the properties of the fluid. That's it. You don't, no specification of additional constants, no tuning factors, nothing. It is the simplest approach in that sense, conceptually. And it is unrivaled in accuracy because if you do it properly, and I have to say this, if you do it properly, meaning if you have a grid that is fine enough to resolve the Kolmogorov scale, it is the most accurate approach out there, right? But the problem is the cost is extremely high and the computing requirements increase so rapidly with the Reynolds number that you have to limit this approach to relatively lower Reynolds numbers. Still turbulent, but relatively lower Reynolds numbers. Because as the Reynolds number keeps increasing, the computing cost keeps on increasing significantly. So for DNS, what we want to do in this class is we want to discuss direct numerical simulation in the context of homogeneous turbulence and try to look at the challenges associated with it. Try to look at the criteria, especially related to the cost of DNS. But we want to look at that in the context of homogeneous turbulence because it is the simplest form of turbulence. You have none of the statistics are dependent on space, and what we know is that for homogeneous turbulence, what are called pseudo-spectral methods are the preferred numerical approach because of their superior accuracy. So the reason why we are picking a simple problem is now if we can make certain assessments about the cost, for example, associated with actually doing a DNS. So for a simple problem like homogeneous turbulence, if the cost is X, then obviously for a more complex problem like jet flows or pipe flows which are turbulent, the cost is going to be say 10x, 2x or 5x. Definitely is going to be more than X, right? So that's the reason why we pick a simple problem. The other reason is homogeneous turbulence statistics are not dependent on space. So the problem is relatively simple to analyze. We look at the reason why we are looking at pseudo-spectral methods for this is spectral methods, as we had discussed earlier, solves the Navier-Stokes equations exactly in spectral space. I'll discuss in detail what pseudo-spectral methods is, but the spectral methods, technically they have infinite accuracy because if you use the right number of Fourier modes, you don't have any truncation error. You have zero truncation error. By that token, they are the experiments of computing in the sense that they have no error. They have zero error. They can only be applied to homogeneous turbulence. So that's another reason why we are picking homogeneous turbulence, because pseudo-spectral methods can only be applied. Now the reason why we are picking a method that has zero accuracy is because then we can look at everything else, assuming this is the most accurate it can get. Then we can look at the cost, then we can look at the completeness, the ease of using it, what are the grid points, or in this case, what are the number of Fourier modes that need to be taken. We can look at it just leaving aside the issue of accuracy. That's why we pick this particular problem and this particular method. Okay, so pseudo-spectral methods. Now if you take a DNS of homogeneous turbulence, the solution domain is a cube of side L. It's a cube, each side is L, and the velocity field is represented as a finite Fourier series, right? We've seen this earlier. U of xt is summation e to the I kappa dot x u hat. U hat is in Fourier space, this is in physical space. So this is in physical space, and this is in Fourier space or spectral space, right? Now since it is a cube, I have the same size in all directions. So I have a cube, L, L, and L. Again, a very simple domain. I'm making life simple by looking at a simple domain, so everything else is straightforward to analyze. N cube wave numbers, what do I mean by that? N wave numbers in each direction. So N cube wave numbers. And here, the N wave numbers, the choice of N depends obviously on the Reynolds number. Typically in homogeneous turbulence with Fourier methods that are used, N is a power of 2. So 32, 64, 128, 256 and so on. Now in magnitude, the lowest non-zero wave number is kappa naught 2 pi over L. Okay, we had seen that earlier, where capital L is the characteristic length scale. So your lowest wave number is 2 pi over L, and N cube wave numbers are represented by kappa in bold, kappa naught N, where N is also in bold, and it is kappa naught E1 N1 plus E2 N2 plus E3 N3. E1, E2, E3 are the direction cosines. N1, N2, N3 are integer multiples in each direction. So Ni varies from minus half N plus 1 to half N. So that is how you have your N wave numbers in each direction. Follow me? So in one direction, you have it going from minus half N plus 1 to half N. So that makes up your n wave numbers, isn't it? And your kappa naught is your lowest wave number. That represents the largest length scale, 2 pi over L. This is all done in a cube. So very simple domain. No walls, just homogeneous turbulence, nothing is dependent on space. Simple enough, right? In each direction, the largest wave number that is determined obviously by the lowest length scale that you want to resolve, and that is going to be your Kolmogorov scale. We'll see that in detail in a bit. But the largest wave number, based on the fact that you have now used n wave numbers, is going to be half n kappa naught. Why? Because this is your half n is your largest wave number, right? That multiplied by k naught is your k max. You understand what I mean? It is half n. These numbers here are integers. Your kappa naught need not be an integer. So these integers multiplied by kappa naught becomes your maximum wave number. So kappa max is half n kappa naught. Substituting kappa naught as 2 pi over L, you get kappa max is pi n over L. Okay, so your kappa naught is 2 pi over L and your kappa max is pi n over L. Now let's say you are solving it in physical space. If you were solving it in physical space, you would have the entire domain L divided into n grid points. So L over n is your delta x, isn't it? L over n is your delta x. That's your grid size. So your delta x is L over n. Remember, you're solving the Navier-Stokes equations in spectral space. So you're not really using grid. But you can think of n points being there and your domain being divided into n points, because it is the equivalent of that what we are doing. It is the equivalent of that. So L over n, now if I substitute L using this equation here, L is pi n over kappa max, and then if I substitute that L as pi n over kappa max, I get your delta x is pi over kappa max. That's your grid spacing, which is pi over kappa max. So if you decide your maximum wave number is going to be 128, then your delta x is pi over kappa max. Okay. Now what the discrete Fourier transform does is it gives a one-to-one mapping between the Fourier coefficients u hat and the u for each Fourier mode, for each grid node, for each grid node, as in for each of the n cube grid nodes. Now, fast Fourier transform is just a more effective way to calculate the discrete Fourier transform. So, and that is what is computationally used. So, it is just a mechanism by which how the Fourier transform is calculated. The discrete Fourier transform is more of an analytical method that is obtained to that is used to obtain the Fourier transform. Fast Fourier transform is a method that is computationally used in order to basically obtain the discrete Fourier transform itself, except it is like the name suggests, it's a more efficient way to calculate the discrete Fourier transform. A spectral method involves advancing the Fourier modes in small steps delta t, right? You're solving the unsteady Navier-Stokes equations in Fourier space. So you are getting u hat for every wave number mode, but you are solving that for every time. So you are solving for u hat and you are advancing that in small steps delta t, just like you would do for any other numerical method. Except now you have a set of ODEs. If you remember, what we got is a set of ODEs. We converted our PDEs into ODEs because of the way we have done a Fourier transform. So you advance it in small steps in wave number space. And this is approximately about order of n to the 6 operations. Based on all the operations that are done, it is an order of n to the 6 operations. So that's a lot of operations, and in order to make it more efficient, pseudo-spectral methods are used. The reason for doing that is because doing the entire thing in spectral space. We talked about wave number triads when we had converted our Navier-Stokes equations into Fourier space. We had these wave number triads where you had this double summation over two different wave number vectors, kappa prime and kappa double prime. You can go back to the previous classes and you can see. Those are computationally very expensive, and as you can see, the number of operations is about order of n to the 6 because of this wave number triads. So to avoid this large cost, we have pseudo-spectral methods, and here it's called pseudo-spectral because it is not fully spectral. And the way we do that is the nonlinear terms in the Navier-Stokes equations, they are evaluated differently. So we have these Navier-Stokes equations in Fourier space. What we do is we take the nonlinear terms, the convection term or the inertia term, take that back into physical space by taking your inverse Fourier transform. Evaluate that in physical space, then transform back into Fourier space and then solve it along with the equations. That is why they are called pseudo-spectral methods, because they are not fully spectral. So that's what is given here. The velocity field is transformed into physical space, the nonlinear terms are formed, and then they are computed in wave number space. What happens is, as a result of this conversion, the procedure requires of an order of n cube log n operations. So now you have significantly reduced the number of operations done because of this switch into physical space. But unfortunately, by doing that, there is an aliasing error that must be removed as a result. Okay, so that aliasing error happens because you are going back and forth between a physical space and a Fourier space. Because of that, there is an aliasing error. And that aliasing error has to be controlled. So there needs to be a method applied for that. So now we will discuss the computational cost associated with all of this. So we discussed the direct numerical simulation. We discussed how spectral methods are used here. And in the context of all of this, we'll discuss the computational cost. So the main numerical and computational issues associated with pseudospectral methods are the time stepping strategy, the control of the aliasing errors. The aliasing errors arise because of the switching between spectral space and physical space. And obviously, finally, the implementation on distributed memory, right? You are not going to run it on a single processor because it would take forever. You're not going to run it on a single core. You will have to run it on multiple cores. That means the program that you're using, the code that you're writing, has to be able to run on multiple computers simultaneously. That is what we mean by distributed memory parallel computers. So one of Rogallo's paper in 1981 deals with a lot of these issues, discusses these issues in details, and it in fact forms many of the basis for many of the DNS codes that are out there on homogeneous turbulence. That book is closely followed. Many issues such as aliasing errors, computational costs associated with these methods, and the time stepping strategy all are discussed in Rogallo's paper, a 1981 paper. It's a seminal paper that is followed by a lot of people writing codes on DNS codes on homogeneous turbulence. So the cost is pretty much determined by the resolution requirements, right? The box size has to be large enough so that it represents the energy containing motions, and the grid spacing has to be small enough such that it represents the Kolmogorov scale, the dissipative scales. Also, the delta T that is used to advance the solution is limited, unfortunately, by accuracy. So if you have a very small delta T, you will have to run it long enough. So that delta T also determines the cost. So these three things, the box size L, the delta X, and the delta T, right? You cannot have a small box just to reduce cost. So you need to have a box that is large enough to such that it contain even the largest length scales, and you need to have a grid size that is small enough such that it can represent the dissipative scales, and the delta T should also be small enough so that it is temporally accurate. So for isotropic turbulence, a reasonable lower limit on L is 8 integral length scales. We can say that L is 8 times L11, and this comes from, we did an analysis a couple of modules back where we looked at where the energy containing scales were, and we realized that it was from about 8 times, 6 to 8 times the largest length scale, right? And then all the way to, it was, I believe it was 1/6 L1, 1/6 L0. So 6 L0 to 1/6 L0 was the range where the energy containing range was. So this is pretty much comparable with that. So 8 times the integral length scale. So that means in terms of the lowest wave number, kappa naught L11 is pi by 4. How do I get that? Because kappa naught, as I had shown earlier, is 2 pi over L, right? 2 pi over L. So if I just substitute that here, right, kappa naught L11 is 2 pi over L, L11. And L11 over L is 1 over 8. So 2 pi over 8 or pi over 4. So this is your criteria of how big, what your lowest wave number should be. So your lowest wave number would be pi by 4 L1. That would be your lowest wave number. So kappa naught would be pi by 4 L11. So if you know your L11, your integral length scale, then you can just calculate the lowest wave number as follows. Now the fact that we are using the Fourier representation of the velocity field, that means you will have to implement the periodic boundary conditions in all directions. But we knew that we are using homogeneous turbulence in order to illustrate what issues about the computational cost, in order to discuss computational cost. So we have chosen a simple problem. We understand that only periodic boundary conditions apply. But at least if we understand, if we have a discussion and if we understand the issues related to computational cost in the context of a simple problem, we know it is only going to get more and more complex for more complex problems like jet flows or pipe flows or channel flows and so on. So I hope this is clear. We will continue issues related to the computational cost in the next class when we look at it in detail on how much does it take, what is the cost associated with doing direct numerical simulations at very specific Reynolds numbers. Thank you.